Okay. So here's what we were looking at last time. We were trying to find a particular solution to this differential equation. We had previously dealt with something like this, where you have a exponential times a constant vector, and the guess was exponential times constant vector, and that worked most of the time. But recall that the problem happened when the coefficient in the exponent was an eigenvalue, right? If that's the case, then this matrix here is singular, and there may or may not be solutions here. In fact, probably there won't be solutions. So what do we do in the case that this is an eigenvalue? And notice here that coefficient in the exponent is an eigenvalue of that matrix. We'll recognize that matrix as one that we spend a lot of time with. Okay. So our attempt was to add in a second term, an additional term, to create the opportunity to hopefully break the stalemate. Right? We're sort of stuck, unable to solve the system in the previous approach. But notice that when you take the derivative of this new term, one of the resulting terms is an exponential times a constant vector, right? And that's an additional degree of freedom, and that's an additional ability to hopefully make everything work out. Okay, so you take your new guess, plug it in to the equation, see what it turns into. It turns into this, as usual. Cancel the common factor of the exponential. Regroup by powers of x, and here's where we ended last time. We have these two equations here to try to solve. Okay, so we're just going to pick up now from here. We'll start with this equation. It is not hard to persuade yourself that the solutions for this b are all multiples of -1, 1. Well, we recognize that as the eigenvector for that eigenvalue for this matrix, right? And so we know that is what that null space is. Temptation is to say, hey, look at this. This is a singular matrix. I've got a free variable here. I can pick any value that I want for k. It's nice to have that kind of flexibility. What value would I like to use for k? Oh, golly, I can choose any value. You know what I really like? I really like integers. Let's just pick, how about k equals 1? Wouldn't that be nice? Right? There is a temptation to just pick a value of k. And you've got to resist that temptation for the moment. The reason why is whatever you pick for your k, and therefore your b, that's going to determine what the right-hand side that you're dealing with in this equation. And that equation, this is a much harder problem. The first equation we were looking at was a homogeneous singular, which always has infinitely many solutions, and that's great. Here we have here we have non-homogeneous singular. Here we have an existence problem. Right? I mean, if we just pick some random b, we've effectively got a random right-hand side here. This is a singular matrix. Probably this will not have solutions. And that's not acceptable, right? If we want to solve this whole problem. So here's the idea. Then don't just pick a value of k. Don't just I like integers. Don't just do that. Leave k undetermined. You plug that in there. Now you've got some flexibility on your right-hand side in that system. Figure out. I'll show you the details momentarily. We're going to try to figure out what value of k would make this system actually have a solution. Most values of k, it won't. We're going to find that one value of k where it does. Okay. So, recopy. There it is. Notice all I do is just plug in for what b is there. So this is the same equation. And let's rewrite. We know what a minus 4i is. Rewrite like that. Notice I've shifted things around on the right-hand side a little bit, not much. So this is what we're trying to solve. We'd like to know for what values of k does this system have solutions. You may even recognize this kind of a problem. Way back in Chapter 1, there were several questions of the form, okay, here's a matrix system, you've got a left-hand side, and then on the right, there's some variables, like, I don't know, A's, B's, and C's, or whatever it was back in Chapter 1. And then the question was, how do you pick the variables on the right-hand side in such a way that you'll be guaranteed to have solutions? And the approach we took there was, look, there's an easy way to decide if a system has solutions. Row reduce it, see if there's any contradictions. Right? So in chapter 1, well, let's say it this way. A chapter 1 approach to this would be row reduce. When you row reduce, you'll end up with a row of zeros on the left. Well, of course you will. We know it's singular. And then whatever you end up with on the right, across from the 0, whatever you end up with on the right, that better be 0 in order for there to be solutions. Otherwise, you have a contradiction. So that's a perfectly fine way to do it. No problem. Let me show you a different way to do it. Has some nice advantages. No row reduction in particular. Let's look at the left-hand side here. Notice that the left-hand side has the feature that the top row and the bottom row are in a 3-to-2 proportion. When you multiply this matrix by A, the result will be in a 3-to-2 proportion. So this vector, these coordinates of that vector have to be in a 3-to-2 proportion. So that's the observation. No row reduction required. Here's another way to say it. Note that the column space, and therefore the image of our original matrix, that column space is clearly all multiples of 3, 2. That means that I need my right-hand side in order to be in the image. In order to be in that column space, I need that right-hand side to be a multiple of 3, 2. This is what it would mean to be a multiple of 3, 2. So, take your preference. And of course, this equation is really easy to solve for k, and you see k is 4/5. So, k equals 4/5 is the only value that makes that equation on the right have solutions. Here, oh gosh, can I fit this all in? So this value of k, that's the only value that will make B allow this equation to be solvable for A. Let me pause for questions. Does anybody have any questions about this? Everybody happy? It's all over but the details at this point. So we know K, right? K is 4/5, so therefore we know what B is. Once you know what B is, then you know this system. You can write out the details, and this is what that system turns into. And solving this system is no problem. In fact, this is really only one equation. Well, it's a 2x2 system, right? But it's a 2x2 system that we know is singular. That means that when you row reduce it, you're going to have an equation followed by 0 equals 0. So this is morally just one equation. And if you write it out, this is what that equation is. And you really do have a degree of freedom here. There's no hidden follow-up trick. You can pick any vector that satisfies that. Whatever you find most convenient. I like this one. And there you go. There's your A. We previously solved for B. And there's our particular solution. Okay, so big picture. What's going on with all of this? Guess and check, recall, is a pretty good way to find particular solutions. We saw last time an example like this. And our right-hand side suggests trying that form. Plug in, solve for your details. Usually this kind of thing will work. Different guess here. Here you have an exponential times a vector. Different guess. Right? Sometimes when that works, well, you've got to refine your guess. Here we have a slightly different guess. Right? But guess and check will usually work, and I tend to encourage students to do it that way. Okay, everybody happy with this stuff? Moving along now to 6.5, our last section. So we're going to start with kind of a flashback to to chapter 4. Look at these kinds of equations here. You'll recall these from way back when, and I'm going to make a controversial statement about this equation, and that is that every term on the left is at most a first derivative. That seems on its face to be wrong, but I didn't say of y. Right? Technically, I mean, this is a smart alecky observation, and I think this is a nice way to think about it, but smart alecky though it is, y triple prime is a first derivative of y double prime. All right? So again, it seems like a silly thing to say, but it is, you got to grant me a first derivative. Okay, how can we turn that into something useful? Well, I can take these three things whose values or derivatives go into, all these terms in this equation. These three things, I can just give them names. I'm going to call them U0, U1, and U2. Right? And I can recognize that, U0 prime is U1. Right? You can see it right there. And U1 prime is U2. You can see that right here. And U2 prime, wait a second. U2 prime is y triple prime, which is right there, and I can solve for it. Right? U2 prime is all of this. So look what I've got all together. Now again, this is a silly smart alecky observation, or so it seems. All together, I have a first order system of equations. This is a first order system in U0, U1, and U2, and their derivatives are given by these formulas. That's a first order system. That's a chapter 6 style system of equations, and I can rewrite that, of course, this is just for sort of aesthetics. It's the exact same thing, but just kind of, written more like we typically write it. Okay, so let's take stock for a moment. What have we accomplished here, if anything? We started off with a chapter 4 style third order equation, and we have turned it instead into a chapter 6 style first order. Right? Third order has become first order. We've reduced the order of the question from 3 to 1. That's phenomenal at a glance, right? I mean, something really nice about that. Third order is harder than first order. We've turned a third order into a first order. That's a good thing. Okay, yeah, but confession, that was only one equation. It's a lot easier to just look at one equation. Right? Here, I've got 3 equations, and worse, it's not just 3 separate equations. This is 3 coupled, highly interlinked equations, and systems are a lot harder to deal with. So there's kind of a pro-con situation going on here. Let's think about which one would we prefer to do. In the former case, if we're doing this, we have to write down the characteristic polynomial. That's easy. You just copy the coefficients, right? You got to find the roots. Okay, there's a certain amount of effort there. But once you know the roots, you write down the solutions. There's explicit formulas. What do you do if there's a multiplicity? Hey, no problem. We've got formulas, right? You just multiply by x so many times, right? All right. Just for, again, comparison purposes, how would we proceed with this system? Well, we've got to, step 1, write down the characteristic polynomial. Okay, well, yeah, that's going to be a little bit of a thing now. This isn't a recopy problem. Writing down the characteristic polynomial, I've got to look at this matrix of coefficients, subtract lambda along the diagonals, and take a determinant. It's doable, but it's a little effort, right, to write down the characteristic polynomial. Again, you've got to find the roots. That's, of course, you've always got to, find roots. What do you do with the roots of that characteristic polynomial? Well, those are your eigenvalues, and now you've got to find the eigenvectors. That's kind of a pain. You can't just write down some formula, right, from chapter 4. You've got to find the eigenvectors, and you've got to hope that you find enough eigenvectors. If you don't find enough eigenvectors, your system's not diagonalizable. You've got a Jordan problem. How are you going to find those Jordan basis vectors? I mean, you can do it with a computer, but it's a lot more trouble, frankly, to deal with this first order system. So, from a computational standpoint, which of these would you rather do? I'd rather do that one. So, that being said, what we have shown is that we have a way of taking a problem that we already know the answer to, and we have successfully turned it into a harder problem. Yeah? Everybody see that? Okay. All right, so that makes us wonder, why on earth would we care? And there's a great answer to that question that I'll get to in a couple of minutes. Before I do, I want to show you something very surprising about these two different questions that we've related like this. First, this question. Recall we have this process for writing down its characteristic polynomial. Now, when you convert to the corresponding first order system, we've got a different, less convenient process for writing down its characteristic polynomial. These are two different questions. Right? This one's got a characteristic polynomial. You get this new characteristic polynomial by going through a weird process to find the corresponding system, then another weird process involving determinants to get to the characteristic polynomial. It seems like these should be totally different characteristic polynomials. The very surprising, at a glance, very surprising result is these are always the same. So this first characteristic polynomial, this second characteristic polynomial, always equal. And that's a real surprise. One detail, one of these might be a multiple of the others, and the way I deal with that multiple is, notice I've insisted that this first coefficient has to be 1. Anyway, that's a minor detail. Okay. Let's see this in action, right? How could this possibly be true? We'll start with this equation here. Characteristic polynomial is easy to write down. Again, in the chapter 4 context, you just kind of recopy the coefficients. It's really easy to write down characteristic polynomials. Here's the first order system that you get. Now, I want to encourage everybody to do this on your own. Think through, how is it that this equation involves nothing but, at most, first derivatives, right? What little smart alecky smart alecky tools do you need to be able to, for that to be, well, I'm going to need to have y, but I'm also going to need to have y prime. So give those names, call them like u0 and u1, or if you prefer, u1 and u2, and write out the corresponding system. I claim you'll get this. Make sure that you can do that. It's good practice to make sure that you can actually implement the method. And then let's play the usual game. We will take this matrix. We will subtract lambda on the diagonals. And then you go through and take the determinant, that whole show, right? And what comes out, well, amazingly, same exact polynomial. Everybody okay? Okay. Now, I like to take, this is largely for dramatic purposes, but I like to take the point of view when we first see this, that this is surprising. And it's surprising if you look at it from a sort of a process standpoint of how do you get from the initial list of coefficients, what is the, step by step, what are all the things that you do to get to the new characteristic polynomial. And there's a lot of steps there that are very hard to kind of see through. And so from a process standpoint, this is very surprising. But let's take a different point of view now. I claim that from an appropriately different point of view, not only is this fact believable, it's kind of obvious. And I just think it's fun how this fact goes from seemingly implausible to borderline obvious if you just take the right point of view. And here's the right point of view. Let me remind you what we did here. We started off looking at a Chapter 4 question, and then we turn it by a certain process into a Chapter 6 question. And what I mean by turning it into, the big idea is that these solutions and these solutions are the same. I mean, you look back to the previous page, the whole point to doing this was that I can instead of solving this equation, I can instead solve that system. Specifically, if I have a vector that solves that system, then y, the first coordinate of that vector, will solve the original equation, right? So that's when I say that these have the same solutions, what I mean is, with the understanding that the solution to the one is the first coordinate of the solution to the other. Okay. So when I do this conversion, the solutions are the same, interpreting appropriately. And now let's just trace that back. Where do these solutions come from, right? So where do these solutions come from? Solutions to a constant coefficient Chapter 4 style equation. Well, they come from the roots of the characteristic polynomial. Those roots come from the factors. Those factors come from the polynomial itself. So effectively then, the polynomial tells you what those solutions are going to be. Okay, now what about in Chapter 6? Where do these solutions come from? Well, there's a long, complicated story about diagonalizability and Jordan vectors and, my gosh, right? One way or the other, though, those solutions come from the, I'm going to generalize and say, the Jordanization of the matrix. Sometimes diagonalization as a special case, but in general, the Jordanization is all about the eigenvalues and the resulting, pick the appropriate basis. But so the solutions come from the eigenvalues. The eigenvalues are the roots of the characteristic polynomials. Roots come from factors. Factors come from the polynomial. So it's the same thing. So why is it that these two polynomials are the same? Well, they better be the same. They've got to give you the same solutions, right? They've got to therefore have the same roots. These two polynomials to two totally different questions, they've got to have the same roots. Therefore, they've got to have the same factors. They really ought to be the same polynomial. Now, there's details to worry about here about, what about multiplicities and, powers of x. And I don't want to get into the weeds about this, about the details. But the broad stroke here, I think, is highly instructive, and this is really very much the point, that it's not at all surprising that the polynomials are the same. The fact that the polynomials are the same is highly connected to the fact that, well, the solutions have to be the same. Okay. All right. Now, this still does not answer one of our earlier questions, which was, what's the point? Right? Very often we find ourselves wondering, why would I ever do this? How does this make my life easier? How does this help me solve problems that I couldn't solve before? How does this make solving something easier? And as of the moment, it remains that what we have is a method of turning an easy question that we already know how to deal with into a harder question. And that does not seem to have much value. So what I'm about to show you, this is not a rare story in math. I'd like to encourage you all to keep your eyes open for this kind of thing. Here and there, it comes up pretty regularly in math, and that is that just because something does not appear to be useful at a glance doesn't mean that it won't be useful in a different context. All right, we have done something that's what I like to call an eyebrow raiser here. We have confession. Yeah, this is a harder problem, right? But we have turned one kind of problem into a completely different type of problem, which has certain advantages, conspicuously that it's only first order. So whether this adds up to a win is not the point. We have accomplished something unexpected. And doing something unexpected in another context may actually be valuable. And here's that other context. A new kind of question I want to consider. And that is something like this. What if we have a second order system, you might call it? Second order because there's second derivatives, right? System because there's two different equations. How would I solve this? And how can I find the y1 and the y2 that make both of these equations work when these equations have second derivatives in them? Well, nothing that we have done before today helps us immediately get started on this. Right? Everything that we've done in Chapter 6 up to now, before today, has been first order only, strictly first order. Useless against this problem at a glance. Okay. And then we think, oh, hey, yeah, but higher order stuff, we totally did second order stuff back in Chapter 4. Chapter 4 we did second order, third order, nth order, right? Yeah, but that was strictly one equation at a time. Strictly. Right? This is a system. And again, this is very importantly, this is not two separate equations. This is one of those linked things, right? The y1 equation has y2's in it. And y2 primes. And the y2 equation has y1's in it. These are unavoidably coupled. Chapter 4 does not address this either. Right? So before today, we had no foot in the door. We don't even know how to start this question. And now what I'm going to do is I'm going to take the idea that we did on this previous page, this kind of, smart alecky, ultimately useless observation of turning an easy problem into a harder problem. Let's apply the same smart alecky observation here. I ask, is everything here at most a first derivative? And to say that differently, what functions would I need to use in order to be able to correctly assert that everything here is at most a first derivative? And, well, I would need y1, y1 prime, y2, and y2 prime. Everything in that given system is at most a first derivative of one of these things. Let's give them names. I'm going to call them U1, U2, U3, and U4. Right? I'm going to write down the derivatives of U1, U2, U3, and U4. Let's think these through. What is U1 prime? Well, those two equations right there tell me that U1 prime is U2. Right? Likewise, these two equations here tell me that U3 prime is U4. And then let's see here now, a little bit more annoying, but not terribly different. What is U2 prime? Okay, there's U2. That means that U2 prime is, it's Y1 double prime, and there it is. Y1 double prime is this thing, which then goes there. Right, and likewise, what is U4 prime? Okay, well, let's see, U4 prime. Here's U4. U4 prime is Y2 double prime. The Y2 double prime is that which is this, which therefore goes there. And look what we've got now. We have an alternative question. Instead of solving this second order system of two equations, we now have the alternative of solving this first order system of four equations. All right, now is this a win? Well, back here, this was not a win. The very first time we applied this smart alecky idea of, hey, check it out, everything's at most a first derivative. That little smart alecky idea turned an easy question into a harder question. Useless. But in this context, it has turned a question that we have no idea how even to get started into a question that's, kind of inconvenient, but totally doable. It's just a matter of, you got to play the game and find the eigenvalues, and fingers crossed, I hope it's diagonalized, but it's doable. We've got methods. Like I say, very often this kind of thing happens in math, that tools that are not useful in one context are indispensable in another context, and that's what's going on here. How we doing? Everybody on board? Okay. I'm going to show you one last thing really quick, and that is in section 6.6. And I know 6.6 is not on the syllabus. There's really no new ideas in section 6.6. It's just examples of how you can capitalize on what's in 6.5. So I just want to show you an example. I'm going to skip the details. Again, you're not really responsible for this. Don't think of this as new material to learn. Think of this as an example of how you can use what you are responsible for, namely 6.5. And so here we go. You'll recognize our old previous story of a mass on a spring. Right? And but now to that mass on a spring, we're going to attach another mass on a spring, like that. And yikes, right? We're going to take this thing and we're going to kind of stretch it down, and we're going to let it go, and we're going to, oh my gosh, right? It's going to do some. Just imagine what would happen with a mass on a spring on a mass on a spring. It's seemingly chaotic and unpredictable, right? It's not at all unpredictable. This is highly modelable. Let me show you how to do the model. It's not that big a deal. We'll start with this first mass. Notice that this spring pulls that way. This other spring pulls it that way. That gives you these two terms. The first spring pulls it up. The other spring pulls it down. You can talk about, friction forces on both of them. You can talk about possibly external forces. Altogether, though, F equals ma on both of the masses. You just write down the spring forces, the friction forces, and the external forces, and altogether you have, if you got to move things around, collect some terms appropriately, but what you have is a second order system of equations, just like in the example that we saw a couple of pages back, that we now know how to solve. We know how to solve this second order system by turning it into a first order 4x4 system and applying 6.3 techniques, 6.3 and 6.4 techniques to solve this system, and totally works. So anyway, I think that's a nice application. Everything else that follows is kind of special case. It's highly supplemental. You're not responsible for these last 2 pages. I guess it's 3. These last 3 pages you're not responsible for. This is the last example I wanted to show you. So perfect time, and I went a minute over. Sorry about that. I enjoyed having you all in Math 216. See you at the final in 1 week. Have a good one.